Good. So we got to just wait for our committee member, Erin Brooks. Get started without him.
I was just on a conference call with him all morning, so he should be here.
That's probably why he's behind.
Well, he's eating his lunch.
Hey, Erin. That was waiting for you. Yeah. All right. Let's get started. So, good afternoon. Welcome everybody to the defense of master's thesis. About a 30-40 minute presentation, the kind of questions if anyone has, and then the committee will need to finish this up. So in 2018, Paul was received an award, a Golden Opportunity Scholars Award from the Soil Science Society of America to attend the annual meeting, and where he met Dr. Jody Johnson Maynard. She was doing a good job recruiting students, and suggested that he think about coming to the University of Idaho for grad school. Paul was a student at University of Wisconsin, River Falls, where even as a freshman, he went in as an environmental science major, which I believe he completed in that major. But even as a freshman, he developed a passion for soil science, pursued that in many internships while there. And he knew he wanted to go into grad school in soil science. And Jody suggested, hey, University of Idaho is a good place. He thought he liked environmental science, maybe contamination issues. And that kind of directed him into my radar, so to speak. And I received some emails, and I believe he came for a visit. And everyone was really impressed with his enthusiasm. And he ended up coming here as a graduate student in the fall of 2019. And at the time, I wasn't taking students that semester, so we agreed. And he was interested in some spatial analysis, doing some of that for his master's thesis. So he started working with Sanaz Shafian, Dr. Sanaz Shafian. She was a professor here, a new professor, doing some remote sensing soils work. And I thought that would be a good match, and I kind of agreed to co-mentor Paul in this project, not knowing very much about remote sensing. Dr. Shafian left for another university shortly after, so I soon got elevated to major advisor. That's exciting for me because I learned a lot on this project, and hopefully I contributed a little to Paul's knowledge over the years. He's been a fabulous student, a great colleague, and I know that because this is a great turnout. And the reason people turn out is because they care and interact with Paul and appreciate him. And so it's been a real pleasure to have him as a student. He's been very active. He's been the coach of the soil judging team and has brought our undergraduate students all over the nation and last couple of years doing soil judging. He's very passionate about that. I've had to remind him that he needs to get his thesis done, and that's all he's second to the soil judging team. But he did it. We're here today. But he loves soil science. I don't know if I've interacted with too many students that love soil science as much as Paul. So that's been really fun to interact with him. And he's done many things, as I said. I just think it's kind of nice to mention a few things that he's not just a student and loves soil science, but Some other things that people may not know about him. He actually spent a semester in Seville, Spain, and study abroad as an undergraduate as a Spanish. This is a really interesting fact. He's an accomplished trombone player. Is that the right way to say it?
Yeah.
So who would have known?
I don't know how you know that, Dan. Oh my gosh.
And he also has been on the UI water polo team, so, which is probably the second soils graduate student we've had on that team, by the way. So Paul, I'll let you go ahead and get started with your 30-minute presentation.
Oh my gosh, thank you so much for that introduction. And I'm gonna. Did you pull my application and resume and however?
I have my sources.
Amazing.
Didn't bring your horn.
No, I haven't played in quite a while, so that's really a throwback for me. So okay. Thank you again for that introduction, Dan. Thank you everybody for coming. Some of you guys have heard at least part of this presentation before, maybe over the last 2 years at seminar presentations that I've given. Some of you may have heard this just last week. I gave the 3-minute version in the 3-minute thesis competition. About a month ago, I gave the 15-minute version at the Soil Science Society of America conference. And I'm excited to finally give this without a time constraint now. So, when I first sketched out, it was 15 minutes of introduction, 2 minutes of results, and another 15 minutes just saying thank you to a bunch of people. So we'll see how I go here. You're here to hear me speak about my research, which I call the use of hyperspectral remote sensing to predict forest soil phosphorus and wildfire ash metal content. One more thing, I did advertise on social media that my presentation would be understandable with a high school science background. So don't be scared off just yet as I walk us through this title and this whole project that I ended up doing. So lots of graduate projects, especially in our department, involve measurements. We've got Jonathan here and Tori on a similar project. This is Tori doing some analysis there. It's some measurements of isotopes and just the nutrients, and how crops are growing in intercropping systems where you grow 2 crops in the same field. Jess is doing permanganate oxidizable carbon, right now, pretty much, carbon in soils and farm fields. Dan Du is doing soil microbial response to antibiotics in soil. These are all measurements. This is how we learn about the world, and that's good. But these measurements almost always involve lab work, and that has its drawbacks. For one, lab work can cost a lot. It costs a lot of money if you send samples away, and it also costs time. Graduate students spend a lot of time doing lab work. This is the UV Viz. You have to sign up to use this equipment. Sometimes lab equipment goes offline. You have to spend weeks to months troubleshooting. It's cost intensive. It's also kind of wasteful. There's a lot of consumables involved in lab work. I just think about the gloves and the vials and the sample bags and the stuff that just gets thrown away to create this data. That's not to mention all the reagents and the hazardous waste that we create and then have to dispose of. And it's also just limited. You can't have lab data for any more samples than you analyze. We try to account for this using sampling strategy, taking composite samples, replicates and duplicates, but there's always going to be more variability in the environment than you can easily measure. So imagine, what if we could obtain similar quantitative data just without doing lab work, instead by taking pictures? This is what remote sensing is all about. You could save the time, the money, and the wastes of lab work. And if you could put a remote sensing system onto a drone, a plane, or satellite, you could massively increase the spatial scale of any study that you do. Instead of sampling just a couple points in a farm field, you could measure some property for the entire field, for multiple fields, for entire landscapes. Clearly, there's a lot to like about remote sensing, but it's not always easy to go from images to environmental data. The data in remote sensing is totally based on the electromagnetic spectrum. These spectral regions are hopefully familiar, right? You have X-rays, which are really intense, high energy, ultraviolet, the visible range, and infrared getting lower decreasing energy. Just as human eyes perceive color based on the wavelengths of light that any given object reflects, remote sensing systems work in much the same way. It's all about wavelength reflectance. Except fancy cameras and detectors can observe way more than just the visible range, what humans can see. So we can think of a digital camera, for example, as a remote sensing system. How a digital camera works is it collects 3 values per pixel in a digital image. 1 value over these blue wavelengths, a second for the green, and a third value for red. These red, blue, and green values are put together for every pixel in the image. And with those 3 layers, then you would say it's a multispectral system. The cameras and detectors that we use for remote sensing can observe much more than just the visible range of the spectrum, usually up to 200 or to 2500 nanometers, which is well into the infrared region. So these systems also have a much greater spectral resolution. So instead of taking just 3 bands or like groups of wavelengths together for red, blue, and green, they can take a separate value for maybe every 3 nanometers or 10 nanometers. This could be hundreds or maybe even thousands of individual bands or like values per pixel in an image. So this is an example of some hyperspectral reflectance data. The y-axis here is showing the reflectance of light out of some maximum, 100% or 1. Something that's lightly colored like snow will reflect a lot of light and have a high reflectance. Things that are darker like water, soil, and vegetation like land are much lower. They're down here at the bottom end. So if you look closely at the x-axis now, the wavelengths, especially if I do this, you can see just how little of this range is visible to human eyes. So it's a small portion of the range and also of the variation within these sample spectral curves. So while it may not seem realistic to measure chemical properties in like soils or samples through just these images, these wavelengths of light, it's important to remember that these hyperspectral systems can detect. They just collect way more data than our eyes ever could. So here's the device, the hyperspectrometer that I actually use to do this measuring. It works by taking in light through this probe tip right here. And light is transmitted through fiber optic cables and the steel cable into the instrument where a readout is produced on this laptop. So this isn't a lens. It doesn't really take an image. It's essentially like a 1 pixel image or just a reading of the light reflected off any surface that you're pointing it at. And that becomes the reflectance. This palm grip attachment here can make field work really easy. You can load this whole system up into a backpack, carry this laptop out. Every time you click the space bar, you get a reading of whatever you are pointing this probe tip at. So it's very simple to use to collect data, but there's also a lot going on. So very user-friendly in my experience. So this brings me to what I'm actually going to do with it now. I have 2 different objectives: to use this hyperspectrometer to predict soil phosphorus in the Lake Tahoe basin, and second is to predict heavy metals in wildfire ash. So this is where I would love to show photos of me at Lake Tahoe collecting these soils, but unfortunately I inherited this data set. So I've still never been to Lake Tahoe. I do know a few things about it though. It's in like California, Nevada on the border. And water quality is a big point of pride there. Lake Tahoe is a very large lake with a relatively small drainage basin, which is why it's so pristine just in general. However, phosphorus is a threat to water quality. As phosphorus gets into surface water, it can increase like algae growth and just decreasing the water clarity and quality in general. So that's pretty common all over the place. And with increasing development in the Lake Tahoe basin and also influence from wildfires, we're increasing the amount of soil erosion and also the phosphorus loading into the lake. I also know that there's a lot of diverse paramaterials and just landscape types within the Lake Tahoe basin. Paramaterial is just the sediment that any soil forms from. And it's probably my favorite part of soil science in general is paramaterial. In Lake Tahoe, there's granitic paramaterials, like granite bedrock, andesitic or basalt, like igneous volcanic paramaterials. There's glacial sediments, there's river sediments or alluvium. all kinds of different stuff. There's meadows and there's forests, and these were all sampled by the prior studies. One of these prior studies was by a master's student under Dan named Tom Heron, who finished before I started, but he did a traditional soil chemistry study. He was interested in the phosphorus in Lake Tahoe, and not all phosphorus is created equal. He was looking at multiple different like species of phosphorus. There's labile or like mobile through the environment, and also non-labile forms of phosphorus. So he did all sorts of lab work, which is kind of a fair trade, I think. He got to collect the samples and do those sampling trips, but also did the lab work. So thank you, Tom, for your contributions. Some of these chemical analyses included the total phosphorus, the Bray and the Mehlich extracted phosphorus. These two kinds are generally plant available types of phosphorus, and then water extractable. So this would be the most labile, the most likely to leach into groundwater or flow through the water in the soil and end up in the lake. So between Tom's data and another just basin-wide set, we have 282 soil samples. Unfortunately, there's not the same lab data for all of them. So each of these 4 parameters were measured for some subset of the 282 total sample set. So right, my study is essentially attempting to replicate Tom's, like his lab data that he collected using the ASD, just based on the wavelengths of light that these soils are reflecting. To do that, I had to collect the reflectance from each of these soil samples. And you remember from this figure, these reflectance curves, I have to know what the maximum reflectance is. How do I know what 100% of light reflectance looks like? I use this material right here. It's called Spectralon. It's an ultra white, ultra reflective material that we assume 100% of incoming light is reflected off of it. It doesn't absorb anything. You can tell just how like brilliant white it is here in this picture, where it's next to a white sheet of paper on a white table, and it's pretty bright, especially when I put it under this light source here. It illuminates this otherwise dark room. So I can take like a calibration reading with this Spectralon panel, set that as the maximum light, and then as soon as I put a soil sample underneath the light and then take a reading, that will be some percentage of the 100. So this is how I build these curves. This light source emits light all the way from 350 to 2500 nanometers. And this is what the data looks like. This is the 282 samples that I measured, their spectral reflectance curves. If you were to zoom in on any one of these lines, you would see it's pretty jagged looking. It's pretty noisy, it has a low signal to noise ratio. So I have to do some pre-processing before I get started. First, I remove the fringe wavelengths. So especially here at the low end, you can tell just how noisy this data is really. It's up and down, it's all over the place. It doesn't really make sense to have something reflect less than 0% of the light. It can't absorb that much. So we just remove them. It's very standard practice in the literature. And then I also try more transformations, including a Savitsky-Golay smoothing filter to really kind of smooth them out. The first derivative, a multiplicative scatter correction, standard normal variate, a log 10 of the data, the reciprocal of the data, absorbance, which is the log of the reciprocal, and a square root transformation. So the point of doing all this is to accentuate different spectral features, to package, it's all the same data, but we're just packaging it slightly differently in each way to try to give these models something different to grab onto, to pull out important spectral features, and hopefully it'll increase our prediction accuracy. So now I'm ready to build these models, which I did in 2 different ways. First was with a random forest, and second was partial least squares regression. Random forest is a machine learning technique that's based on decision trees, which essentially take each sample through a series of questions to arrive at either a classification or a predicted number. At each node of a tree like this, yes answers will proceed to the left and no answers take the right. These branches or like paths through the tree end in leaf nodes or like groups of samples that are similar enough that they don't need to be broken down any further. You can take the average value of each of those samples, like the known lab data value that we're trying to predict, take the known value for each sample in the leaf node, average them together, and then that value becomes the predicted value for any new samples that classify through the tree and end up in that leaf node. So if you've been looking closely at this example tree, you may think it doesn't look much like soil data. That's because it's not. This is basketball data. This is a real model that I built when I was first trying to learn how to do this. And this decision tree will answer the question, given some statistics on the Milwaukee Bucks shooting in any given game, how many points did they score? So let's say last night against the Kings, we made more than 39 field goals, but less than 45. So we're going this way. If we make less than 17 free throws, but more than 13 3-pointers, chances are the Bucks scored around 116 points. So is this super useful? The conclusion that the more buckets you get, the more points you score, probably not, but this is it. The concept is the same. So that gave me confidence that I understood what this was, how it worked, and I could use my own data to do it. So the process is exactly the same for the soil samples, except now our inputs, or the predictor variables, are the reflectance at any given wavelength. So these trees are built using some subset of the data, usually about 2/3 of the samples. And then they can be tested with the remaining 1/3 usually to kind of estimate how well that model actually did. So this is great. This is how one decision tree works. This whole process of building a tree is repeated 500 times. Each tree is going to be slightly unique and predict a different value for each observation. And random forest requires you to see the forest for the trees. So you take the average value predicted for each sample across all the trees in the forest. That becomes the new predicted value that I compare against the known, like the lab data value. From there, I plot those two against each other, and then I can evaluate how good of a job this model did to predict the data. To help do that, to help evaluate, I did some extra cross-validating by leaving some samples out of this whole entire process. So I have some soil samples that are unfamiliar to all of these trees, and then I can run them through all the trees, get their predicted values, and that's a good way to see how this model would do on truly unique or truly unknown data on new samples. So that was random forest. Partial least squares regression is the other method I used. It's a little bit less engaging of a concept in my opinion, but it's all about reducing the explanatory variables, breaking them down into some latent variables that kind of take these predictor variables and tie them together. It's similar to a principal component analysis. So breaking multiple, like multi-dimensional analysis, making that work in just like 2 dimensions, principal components. Partial least squares is adapted to for using with collinear data when you have lots of predictor variables that are really correlated to each other, or they're like saying the same thing, which is usually very difficult for prediction models to handle. And also this works well when you have more explanatory variables than observations. So in these hyperspectral studies, you have up to 2,000 maybe predictor variables, these individual wavelengths, and not that many observations or samples that you're trying to predict is what that means. Partial least squares regression, these models are optimized when you can have the lowest error of prediction while using the fewest number of components, or these latent variables. So theoretically, you could have as many components as predictor variables that you have, and that would encompass 100% of the variation. You would completely match the known values, but I don't really know what you would have at that point because that's not a model. That's not a simplification of the reality. So it's a little bit subjective sometimes. I get a readout of what the error is at each number of components, and I have to subjectively choose or decide how many to use. Sometimes like 6 components for a data set might give a good error of prediction, but 12 components is even lower. But you have to be careful because the more components you add, the more complex the model gets, the closer it fits onto this training data, and then the less confident you can be. You have less confidence then in its ability to predict truly new data. So you want to avoid overfitting is what that means. Keep the model parsimonious, or as accurate with as few components as possible. Also, before I get into my results, it's important to probably put in context, I'm not the first person to do a hyperspectral prediction study using soil or even using soil phosphorus. So It's been done before, generally more often with the partial least squares than the random forest. And there's a lot of ways that different authors choose to evaluate their models. Most common with the R squared, which is the coefficient of determination, how closely all these points can be fit onto a line. The root mean squared error, like the ratio of performance to deviation, there's lots of options. I'm going to focus on the R squared because that's the easiest concept, I think, to imagine how tight that line is, that fit is. So if you can have an R squared of validation on these unknown samples greater than 0.9, that's a very accurate model. That's like the ideal result that this one here in the top left observed. That would be great. R squared between 0.7 and 0.9 is a good prediction accuracy. You get into more like a moderate accuracy between 0.5 and 0.7 for the R squared. And then once you're below 5 or 0.3, it's generally not an accurate model. So for my results, remember that I had those 8 pre-processing methods and those 4 soil attributes that I'm trying to predict. And I made a model for each combination. That would be way too many to go through all together. So here are the highlights. For each soil attribute, the pre-processing method that made the best model is shown here. So these R squared of calibration, they're all over 0.9, which is good. It's fitting the training set or the samples that are used to build these decision trees are fit pretty well onto a line. And then when you take the unknown data and try to match those, it doesn't do as good a job, but it's still pretty accurate, around 0.8 R squared for the Bray phosphorus and the total phosphorus, slightly lower, around 0.7 for the water extractable and the Mehlich phosphorus. The multiplicative scatter correction, this MSC preprocessing, ended up being pretty useful for 3 of those attributes. This is the random forest, and then the partial least squares regression, same thing, one model for each combination. And if we look just at these R squared of validation values here, they look pretty good. 0.875, that's really good for Bray phosphorus. 0.5 for the water extractable is getting down there, but it's still all right. The R squared of calibration is a little bit all over the place. So I think this makes the partial least squares results a little bit harder to trust. I think that the random forest, I would trust the random forest a little bit more to be able to predict new data. Another thing to add here with the results is the effect that parent material had on these models. There's one thing I know about model prediction, and it's that as you decrease sample diversity, you can increase the prediction accuracy usually. So I thought that having all these broad or like diverse paramaterial types in the Lake Tahoe Basin, that would add some kind of, you're adding a variable to the soil samples. Maybe they're going to appear differently, spectrally speaking, based on like the mineralogy that they're formed from or what the soil paramaterial is like. And that's going to make it more difficult to predict. So what if I build some models on the left side here without including paramaterial as like a predictor variable, and then while I do include paramaterial, and it doesn't make that much of a difference. I was pretty surprised. I thought it would have a lot more of an impact. This R squared, it's not calibration or validation. I just gave it all of the data. It's just a marginal increase, if anything. It's probably not significant. The model does a good job with random forest, even without paramaterial. And then the partial least squares, it increased a little bit more, but still I won't confidently say that one of these models is better than the other. So I thought that was a surprising result. Moving into my second project or chapter of this thesis, which was about wildfire ash. Wildfire ash itself has a low risk of contamination in the environment, or at least it should. Wildfires are a natural process. They've been happening on Earth as long as there have been forests on Earth, and there shouldn't be anything of concern in this ash as it naturally occurs. However, it's no secret the effect climate change is having on wildfires, especially here in the West. We can expect in the future that wildfires will burn more frequently, more intensely, and over more areas in the future, and also over larger areas, potentially close to developed areas. This is bad because that's both where the people are and also where there's potential contamination. So after decades of industry and vehicle traffic and just atmospheric pollution, there can also be atmospheric deposition of contaminants, including perhaps heavy metals. into these forests. And because they're near developed areas, we've also been suppressing these fires. So wildfires have not been burning as often as they perhaps naturally would. So what that means is we have an increased fuel load and also contaminant load. So when these forests inevitably do catch on fire, there could be some concern for contamination. Now there's potentially some risk, especially if you consider if a forest burns in the watershed of like a drinking water reservoir, and we know how mobile ash is in the environment as well. So as soon as like the wind picks up or it starts to rain, ash will be on the move. It's not going to wait in place long enough for us to go sample it if we think there's a risk of contamination. Bring those ash samples back to the lab and do some analysis on them. It's just going to be gone. So the potential contamination in ash is important to understand for both public health, for wildfire response and resource allocation. And it's also a really good use of remote sensing potentially in the future. So the ash samples that I used are a smaller data set that were also obtained through other projects. They cover 6 states in the Western US and 13 wildfires for a total of 40 ash samples. So this time I did have to do the lab work, which ended up being a multi-acid digestion to like melt these ash samples down and extract the heavy metals out of them so we could analyze them on the ICP. The best results we got, or the like highest rate of recovery for these metals through this analysis, was for cadmium, copper, lead, and zinc. So that is what I moved forward with trying to predict. Here's the raw data, the reflectance spectra again for these 40 samples. And this time it's kind of easier to see the noise, I think, especially at the low end, but also some of this jaggedness. I do the same procedure to pre-process and build these models. And the random forest was much better for the ash than partial least squares was. So we still have good R-squared of calibration here above 0.9. The validation results are a little bit lower than the soil was, as high as 0.77 for copper, around 0.65 range for cadmium and zinc, and lead was just kind of tough, down at 0.35 for the R-squared there. So that's a less accurate model for lead. The MSC, multiplicative scatter correction, was again one of the more reliable pre-processing methods. That was a good one to include. And unfortunately, I'm not completely sold on these results. I feel like 40 samples is maybe not enough to reliably go out and predict new data with. So something must be working if it can build like models that fit a line as tight as some of these appear. Something must be working, right? I'm confident that if we develop this more with just a bigger sample set, more ash samples collected, or maybe ash samples collected in a smaller spatial scale, we could get some good prediction results. It's just a question of how much you trust these models as they currently stand. So it's very hard for me to contextualize these results as well, because I really couldn't find any other studies trying to predict the metal content of wildfire ash using this hyperspectral sensing. So there's some studies out there of heavy metal prediction in soils, but by far the most common is nutrients in soils, like phosphorus. That means we have a gap in the literature and a really great opportunity to develop these models in the future. More work, we could do more work on ash and remote sensing. So just kind of some general conclusions I had is that the visible near infrared reflectance models were generally good at prediction. They had generally good predictive accuracy. The soil samples had a surprisingly low influence from parent material, which I was surprised by, at least. And I feel like the ash samples were just limited by their sample size. In general, as you decrease the sample, and then what can we do with this? What's in the future? My models, I think, are best suited to test new samples. So let's go down to Lake Tahoe. Let's sample more of the soils and then try to predict. See how well they do measuring the soil phosphorus content while also like verifying that with the traditional lab data methods. In the future, it would be great to apply this to aerial measurements. I don't think my models are prepared right now to handle drone, airplane, or satellite data, but that's what this could be in the future. This is where it starts, analyzing these spectral end members, as we call them. I know exactly, this is my soil sample right here. I'm getting a really good reflectance of this soil sample. And that's what it takes to build these models in order to scale them up to measure samples naturally in the environment. I have to acknowledge Sanaa Shafian, as Dan mentioned. She's the whole reason we have this ASD in the first place, and the reason I have this whole project. So even though she left the university not long after I started. Tom Heron was here. He left the university before I even started. I was really thankful to meet him last month at the Soils Conference. I think he's online. He may be listening in. So thank you, Tom, for your lab work, for your field work, and sharing your data, your samples with me. Thank you to Erin and Mariana, who I believe is also online, for maintaining these samples and also with the collection. For the ash, thank you to Tietz and the U.S. Forest Service here in Moscow, the Rocky Mountain Research Station. I use their samples for the ash, supplemented by Scott Shepard and Patrick Jarrett. So thank you to both of you. Thank you, Alex, for helping me with the physical ash analysis. Also, just the professional and the personal support that you provide to me and a lot of other students in our department. And lastly, thank you, Dan, who, my advisor. You didn't have to take me on as a student after Stas left, but you did. You didn't have to help develop this project outside of your main area of expertise. And you definitely did not have to support me as much as you did, as I spent a lot more time teaching and on extracurriculars than my research. So thank you, Dan. And I put this last slide in as a joke, kind of just for you, because I thought you'd take it out. Dr. Bruce Bugbee is a plant scientist, professor at Utah State. And we heard him say this at the Soils Conference last month, that everybody trusts a measurement except the person who made it, and nobody trusts a model except the person who made it. And I thought that was just perfect. I love it. That's exactly what I'm doing. I'm trusting other people's measurements to make my own models. So I just couldn't resist. With that, I'll open the floor for questions. Yeah, thank you guys.
I've got a question.
Of course.
First, I apologize for contributing to your extracurricular activities. It was very, very great presentation, and thank you again for all the help you've been to me. Question, and this is something that bugs everyone across the natural resources realm and sampling variability and sample size. Whole issue of cost versus trying to get an answer. And when you have limited sample sizes, how you subset is really important to help bring validity to your end results. So when you subsetted that 2/3, third, and I'm thinking more on the phosphorus detection, not on the ash side, is how did you go about selecting or randomly selecting those subsets to test? Because when you get small data sets, random sampling oftentimes of those smaller data sets can give you different answers depending if you have a limited sample size. Can you address how you did that?
Absolutely. That's a great question. This is kind of how the testing and training sets are built, right, to make these random forest models, and that's done automatically. It's called a bootstrap aggregation, specifically how these models are done, where let's say I have 100 soil samples that I want to use to build a model. There's going to be 100 samples selected, and the program or the model is not going to hesitate to draw the same sample more than once or leave samples out entirely. So this kind of random process usually ends up having 2/3 or like 66 soil samples are going to be selected either once or more than once. Then the remaining third will not be selected at all. So we have samples that are in the bag that get chosen to build the model, and then the out of bag samples, which is like the calibration that we use to verify. So then you get this out of bag error rate on the samples that were left out. This is just all done automatically. I believe it's different for every tree that's created. So just kind of by brute force, law of large numbers, like with 500 trees in this random forest, you have these samples included or left out. And then when I made this, the further split of my testing sets that I wanted to build all these forests with and then test them later on, I just did that with a random selection. So this is more on the analysis side rather than like the sample collection. Like if I had to go out and choose how to composite or subset samples in the field, that would be a lot more different, I think. I was happy to do it, be able to do it randomly and then also be able to do it multiple times if needed. So thank you for the question, Mark. Anybody else?
Hey, Paul, I've got a question. Yes, it is. But that's not my question. So I actually have two. The first one is, do you need to have bare soil to make accurate measurements?
Do I need to have bare soils to make accurate measurements? Like if we were to scale this up into the field?
Yeah, if you were to actually take it out and say you had some vegetation cover in the Lake Tahoe basin, would you need to clear that?
It's a very good question. So potentially. The way that I collect my data now using the full range of visible and near infrared, not all of those wavelengths are going to be able to view the soil if there's something in the way, vegetation or buildings or pavement or something. So that's why my study worked by collecting those samples in the first place. The idea is that you could potentially identify which wavelengths are most important for predicting the soil, the values that you want, and then those wavelengths could also penetrate through vegetation. So this is how like LiDAR works to measure like terrain maps. You can use specific wavelengths that penetrate through vegetation, but reflect off of the soil surface. So you can get really detailed maps of elevation. When you're using the full spectrum though, that's not the case, right? You'd be able to see what's in the way in the visible range. So that is a good question. That's why I think farm fields are probably the most popular use for these prediction and the remote sensing precision agriculture types of studies, because you can maybe see a whole large area of soil just exposed at the surface. So as they're currently constructed, no, I would not be able to use these models to see through anything. It would have to be bare soil in the field. And then your second question.
Thanks. Yeah, that was interesting about the LiDAR, especially. My second question, does soil moisture have an effect on reflectance? It looked like all your samples were nice and dry in the lab.
They were, I did not mention that. I used air dry samples, saved the 2 millimeters to keep them very consistent. And that's a good question. How would the amount of moisture affect the reflectance? You can imagine, as all the pedology students in here know, that as you spray soil, it gets darker. We collect a dry soil color and a moist soil color. So that's a response in the visible wavelengths of the spectrum. You're changing the reflectance based on the moisture content. So you can research how spectra respond to different moisture contents. There was a study done in the Forest Service about this in ash content specifically. So you take ash samples at different moisture contents. How do the spectra change across different moisture gradients? So that's something to consider, again, for scaling up in the field. Yeah, when you're holding them consistent, you can assume it's all the same. So then maybe in order to prepare for a field study, I could take soil samples and measure their reflectance at different moisture contents and see if there's a way to measure that from the spectra. So you could study the water content, knowing which wavelengths correspond to water in the soil samples, and maybe that's a good way to address the water content as well. So thank you, Maddie. Maddie was a student here in plant science at the University of Idaho. Now she's at Utah State working with Dr. Bruce P. So thank you, Maddie.
Thanks, Paul. It's been fun to see the different time length versions of your experiments.
Yes.
Hey, Paul, this is Mariana Dobre. Really great presentation, and I'm happy to see some of the results from the Lake Tahoe being used in a different way. So that's really, really exciting work. My question is also about the data collection. I saw you showed a photo in a dark room. Do you need a dark room to get accurate measurements, or you can do it in any type of conditions? I mean, the measurements.
I would say indoors, a dark room is pretty important. So when I was first kind of troubleshooting and trying to figure out how this whole system works, I tried doing it just like in the lab with the lights on, and I was getting a ton of interference just in these visible wavelengths. And then as soon as I got to 800 nanometers of this infrared range, it became pretty steady. So that's from the lights, like the ceiling lights emitting visible light, and nothing in the infrared. So that was just adding interference and kind of reducing the quality of the data. So some researchers are really particular about it. They'll say it was a dark room with no windows, with like tape on the door and wearing dark clothes, like no extra reflectance, interference possible. And then I kind of adapted some of that, but not all of it. But then if you can take this outside and you have a lot less control over the light conditions there. So thankfully the sun emits complete full spectrum radiation, but then changing light conditions by cloud cover can make a big difference. So if you take this outside, you have to take this white reference calibration a lot more often, probably with every single sample that you analyze, in case the amount of like the maximum reflectance changes because of just the air conditions or the weather. So I would say that yes, dark rooms are valuable indoors, and the ambient light really does make a difference.
So not only that you didn't go to Lake Tahoe, you also spend a lot of time indoors in a closed room and dark room. Boy, sorry about that. We need to take you to Lake Tahoe somehow. I'll chip in some money.
So Paul,
Thank
actually,
you.
Mark, I just had a vision of you in black, all black, black gloves, black. Anyways, couldn't you just get a little black box with a little door, put your sample in, that your spectrometer can then mount to the
That's
top?
a good way to do it. Yeah, that could be a good way to control the light, as long as you have a way to observe the reflectance, like to have the probe tip and the light source unobstructed and without any other interference. That would be a good way to do it. I
Just
think.
see you have a little mount on the top, a little door, stick your sample in, close the door.
Yeah, when there's one kind of extra piece of equipment that comes with the devices, like it's called a leaf clip. So if you're going to measure plant samples and like just a blade of or like a leaf, take a leaf in general, there's this like clip attachment where it secures on and like holds the leaf right on the tip of the sensor. So you can do that in a greenhouse or outdoors, and it just really controls like this is what the sensor is observing, and there's no other incoming light. So I don't know if there's the same kind of like containment device for samples that you can open and like slide in or not, but that's a creative idea, I would say.
Patent it. Sell it, Billy.
Next objective. Paul.
Great presentation also. I was wondering, can you take your hyperspectral data and using the visible part, convert that into Marcel notation?
I believe that's possible. I believe there is equipment out there that can like digitally measure a Munsell color. Jody's always talked about, which she stepped out, but talk about getting one of those to help like students that struggle with color, especially if they're colorblind. So I don't think that would be very difficult. I have really good high spectral resolution data over the visible range. So if I found a program or developed a program to translate that to Munsell color chips, or if we know what the reflectance is at each one, I think that could very easily be done with prediction models or just the reflectance data in general. So
I know a lot of soil taxonomy is based on soil color, and a very significant portion of males are at least partially colorblind. These are, this is essentially the data set that's gone into some of the color parameters that go into classifying soils. And it just seems like with this type of technology, there should be better ways of characterizing color if you're going to use it as an important feature.
I agree. Yeah, I think that that's a common complaint a lot of students have, how subjective the color books are. And yeah, we're making the rules of soil taxonomy, right, based on color sometimes. So I think you could definitely consider this a quantitative way to measure colors. Good question. Galen.
I have just a visual question. Why was there a dip in reflectance at like the 2000 nanometer range for the samples?
If I show this picture again?
Yeah.
That's a good question. This is around, you can see a little bump here at 1400 and a dip at 1900 there.
Like where is that on the spectrum? The 2000? Is that like in the?
This is all the infrared range.
It's all infrared. Okay.
Yeah, so the visible is going to end somewhere here in just this first kind of section. but that's a great question.
Does that have to do with the color? There's some compound in the soil that's absorbing that like radiation.
At these wavelengths, yeah, it is. So when I was first kind of trying to do this setup in the very first place, I tried taking it outside to like try it with sunlight, and I was getting crazy results. I think we also saw this with Dalton. We went outside just a few weeks ago to try this outdoors, and we saw crazy variation in 1400 and 1900 nanometers. So this is one of like the spectral kind of signatures or fingerprints of water, actually. So the OH bonds in water respond to these specific wavelengths right here, and you can tell you can tell how much water content there is there. So with moisture in the atmosphere, that's where all the variation was coming from. So with these samples, all the same moisture content, the response, like this little bump and a little dip there, is generally pretty consistent. But yeah, if we were going to measure soils at different moisture contents, this is probably where visually I would go to look, is what does the response in the 1400 and the 1500 or the 1900 nanometer range look like. So I believe Sarah Scholes is joined online, or she's the one that taught me that originally at the Forest Service. So thank you, Sarah. I may have some questions in the chat here. I'm going to take a look. Okay, might not be any questions, but thank you everybody for your support. Anybody else? We are almost at 2 o'clock though, so it's all right if not. Jonathan?
Out of curiosity, is this this sensor that you're using, is it an active sensor in that it actually shoots out the desired wavelength at the sample and collects that, or is it a passive sensor in that it's just measuring what's being emitted?
It's a good question. This one's passive, so it takes in reflectance as it naturally reflects off of some other light source, so either the sun or that light bulb that I was using. So really, I could set it up in here and take measurements of like the chairs and the tables and like carpet and get different readings for just what the surfaces are reflecting. So passively.
So if you were to put a hyperspectral on a computer screen, what would it show you?
If like imagery or connect.
Because we know how a computer screen is just a bunch of tiny little diodes that are emitting just a certain wavelength. Would you pick up all those different wavelengths with hyperspectral?
Oh, if I shot, oh, that's a great question. So something that's emitting more light, it would be difficult to do a calibration. So I imagine if I took a calibration of the white reference, so what 100% reflectance looks like just in these ambient light conditions, and then like took a reading off of like a bright computer screen, it would probably be over 100% reflectance because we're adding more light in than we're calibrated for. So that'd be very interesting. It would probably only be in the red, blue, and green wavelengths because that's what every pixel on like the computer screens are emitting. So that'd be cool. I'd never tried that.
Why don't you try that? I'd be curious.
Thank you, everybody, for coming this afternoon.
Great job, Paul.